Okay, our third speaker is not with us today, so we're gonna have the pre-recorded talk on Zoom, I believe. Maybe not.
Thanks so much
Oh,
for inviting me today. I'm so
okay.
sorry I couldn't be there in person. Today I'll share our work evaluating associations between diffusion MRI microstructure measures and amyloid PET burden in cognitively normal individuals, focusing specifically on novel single-cell diffusion MRI models. I have no disclosures to report. For those unfamiliar, these figures outline proposed models of pathological biomarker changes along the Alzheimer's disease continuum. And they show that amyloid deposition precedes neurodegeneration and cognitive impairment, often by many years. Diffusion MRI is sensitive to small changes in brain microstructure and may therefore offer sensitivity to early, more subtle AD neuropathology that precedes macrostructural brain abnormalities that are often highlighted in figures like these. While most diffusion MRI work has focused on the white matter, cortical gray matter is where early pathology like amyloid deposition is thought to begin. Diffusion MRI in the cortex may pick up early amyloid-related microstructural changes like inflammation or edema, cellular swelling, or neurite loss, well before we see gross volumetric changes. We know that the most widely used single-cell diffusion model, diffusion tensor imaging or DTI, cannot accurately measure sources of non-Gaussianity, including restricted diffusion, neurite dispersion, and free water, while multi-shell models can. They may therefore be better suited for studying complex gray matter microarchitecture. However, multi-shell protocols aren't widely available in clinical or legacy research datasets. Single-shell diffusion MRI, on the other hand, is already collected in thousands of existing scans worldwide. So we were particularly interested in evaluating advanced models for single-shell diffusion data beyond DTI. In particular, recent single-shell adaptations of multi-shell NODI and mean apparent propagator or MAP MRI. And these models are called NODI DTI and AMORA, respectively. NODI is a multi-compartment model that parses signal contributions from various tissue compartments like the intra and extracellular tissue compartments, and may therefore offer microstructural specificity. In contrast, MAP MRI is fit to the entire signal and imposes minimal model assumptions, which could mean greater overall sensitivity to histopathological changes. So single-shell adaptations of each of these multi-shell models may each provide some advantages. So our goal here was to evaluate relationships between amyloid PET and novel single-shell cortical microstructural measures in cognitively normal individuals that we pooled from 4 studies of aging and AD, all with varying single-shell diffusion MRI protocols. In total, we studied 769 cognitively normal individuals that had diffusion and T1 weighted MRI, as well as amyloid PET. PET scans were standardized into centiloids for cross-site comparability. 425 participants also had tau PET data, and tau positivity was defined for each study respectively here. In addition to DTI, advanced single-shell NODI DTI and MAP AMORA models were fit to the diffusion data. And then the 10 mean diffusion MRI measures that are listed here in this table were extracted from 34 cortical regions of interest that we parcellated from T1 weighted images with FreeSurfer. We also evaluated mean measures in the full cortex. For comparison, more conventional T1 weighted cortical thickness measures were also evaluated. Random effects linear regressions were used to test for associations between our regional cortical MRI measures and amyloid PET centiloids. And we adjusted for age, sex, education, ethnicity, and race, total cortical thickness to confirm effects beyond gross atrophy, and intracranial volume. Total cortical thickness was not included when we evaluated regional cortical thickness associations. We used diffusion MRI protocol nested in study as our random variable to account for interstudy variability. We also tested for the interactive effects of amyloid centiloids and tau PET positivity on cortical measures where we initially detected significant amyloid associations. We found limited regional associations between greater amyloid and higher DTI fractional anisotropy and cortical thickness, and that's shown in the top row here. But we found more widespread associations with our advanced diffusion MRI models. Greater amyloid was associated with lower NODI-DTI orientation dispersion index and with higher Amura apparent propagator anisotropy measures, including associations in the full cortex measure. The most consistent associations across measures were found in AD vulnerable regions, and these included the precuneus, the rostral anterior cingulate, rostral middle frontal gyrus, superior and inferior temporal gyri, superior and inferior parietal gyri. We found that only dispersion index was moderated by tau, where we saw that tau positive individuals showed steeper negative ODI slopes with respect to amyloid burden. So our findings suggest a biphasic or non-monotonic trajectory. In early phases, amyloid deposition may be associated with increased diffusion restriction. And while this may seem unintuitive, it could be caused by factors such as inflammatory microglia infiltration, cellular hypertrophy, or large hydrophobic plaques, increasing the number of diffusion barriers in these early stages. And we found that this was not moderated by tau. In contrast, in later stages, we saw that dispersion decreases with amyloid deposition, perhaps as tissue breaks down and neurites are lost. And we see that this is being driven by the tau positive individuals, further suggesting a later neurodegenerative effect. So this really supports several recent studies showing a non-monotonic pattern of these brain MRI changes in Alzheimer's disease. This has been shown with diffusion MRI in the white matter as well as the cortex and T1 weighted features. So to summarize, advanced single cell diffusion MRI metrics are sensitive to cortical microstructural changes associated with early amyloid accumulation. These effects exceeded those found with more standard DTI or T1 weighted measures and were in some cases moderated by tau. But overall, this work supports using diffusion MRI as a non-invasive early biomarker, even when only shorter clinical quality single cell acquisitions are available. But of course, these results are preliminary. In addition to fitting nonlinear models, now that we suspect a non-monotonic relationship, we are in the process of adding several more data sets to increase our sample size. And this will allow us to limit our analyses to amyloid negative cognitively normal individuals to try and really isolate the earliest part of this biphasic trajectory. We will also be better able to probe sex and racial or ethnic differences in these effects. Some of our data sets are also multi-shell, so we really want to validate whether these novel single-shell models are capturing the same effects as their multi-shell counterparts. So all of that is currently in the works. I'd like to say thank you not only to our collaborators, but the participants, their families, and the many people that make these team science projects possible. Please do reach out to me if you have any questions, and I really appreciate you listening today. Thanks so much.
Yeah, unfortunately, we're not going to take questions, so we can move to the next speaker.